Today's topic is disturbances in acid-base balance and its diagnosis. Okay, again, good evening to all of you. Let's start today's topic, that is disturbances in acid-base balance and its diagnosis. Clinically, this topic is very important. It includes in veterinary, analytical biochemistry. You all know Unit 3, analytic biochemistry, or we can say clinical biochemistry. So, what are the acids and base? What are the acids and bases? You all know acid yields H plus ion, HCl gives, you all know H plus plus, Cl minus. Base always yields hydroxy or OH minus ions, or we can say combines with hydrogen ions. Like this, strong acid HCl, H plus, Cl minus. This is a strong acid. It gives weak base, that is called as conjugate acid base pair. Likewise, H2CO3 weak acid gives H plus plus HCO3 minus, that is strong base, HCO3 minus, or we can say H2CO3 dissociates and gives us H plus plus HCO3 minus. This bicarbonate. Am I audible to all of you? What is the definition of acid? Please write in the box. What are the bases? Or we can say alkali, acid and alkali, or acid and bases. Acids, by acids we can get hydrogen ions. By bases we can get hydroxyl ion, or we can say they combine with hydrogen ions, H plus. Okay. So acid is a substance whose dissociation in water releases hydrogen ions. Is it clear? Okay. Addition of an acid to a solution increases concentration of free H plus in the solution. So produces more acidic solution, and this is an important line, that is decrease in pH. It leads to decrease in pH. HCl is a strong acid, you all know. It dissociates into H plus plus Cl minus. Likewise, a base releases hydroxyl ions, OH minus, in aqueous solution and decreases its H plus concentration by accepting or by binding with free hydrogen ions. So it gives bases, or base gives OH minus, acid gives H plus ion. Acid is a substance whose dissociation in water releases hydrogen ions, and base releases hydroxyl ion in aqueous solution and decreases its hydrogen concentration by accepting or binding with free hydrogen. This results in increase in pH of the solution. So acid results in decrease in pH, and base results in increase in pH of the solution. The OH except H plus results in the formation of water. So H plus plus OH minus gives water, a molecule of water, that is H2O. Amphoteric substances, you all know some substances such as amino acids and protein acts as acid as well as bases. So amphoteric substances both act as both acid as well as bases. So is it clear to all of you? What is acid? What is an acid? What is base? Please add in the box. Is it clear? So important definition is acid is a substance whose dissociation in water releases hydrogen ion, and base releases hydroxyl ion and also decreases its H plus concentration by accepting or binding with free H plus, means combines with hydrogen ions. Okay. Now we will Come to the next slide. Acid-base balance. Normal pH of blood is, please write in the box, normal pH of blood is, please write in the box, what is the normal pH of blood or plasma, you can say. Please write in the box that it is 7.35 to 7.45, slightly acidic or alkaline. Please write in the box, it is slightly acidic or alkaline. 7.35 to 7.45. Is it slightly acidic or slightly alkaline? Yes, it is slightly alkaline. Good. What is acidosis? Physiological state resulting from abnormally low plasma pH. You all know alkalosis. Physiological state resulting from abnormally high plasma pH. So acidosis, in acidosis, we can get low plasma pH, and in alkalosis, we get high plasma pH abnormally. So what is acidemia? When plasma pH is lesser than 7.35, and what is alkalemia? When plasma pH is greater than 7.45. Is it clear to all of you what is acidemia and what is alkalemia? Please write in the box, when plasma pH is lesser than 7.35 is called as acidemia, and when plasma pH is greater than 7.45, it is called as alkalemia. So, okay, is it clear to all of you? Now the body has developed 3 lines of defense to regulate the body's acid-base balance. You all know, first, foremost important is blood buffers, second is respiratory mechanism, and lastly by renal mechanism. We have already read this blood buffers, then respiratory mechanism, and lastly renal mechanisms. So the body has developed 3 lines of defense to regulate the body's acid-base balance. So what is a buffer, or what are the buffers? What is the definition of buffers? Solution that resists the change in pH on addition of acid or base. We have already read in the practicals. So is it clear to all of you? What is buffer? What is a buffer? Or what is a buffering capacity? We have already read in the practical classes. Please write in the box. Do you know the definition of buffers and buffering capacity? Okay. Buffers, solution resists the change in pH on addition of acid or base. Acidic buffer, weak acid and its salt with strong base like H2CO3. What is H2CO3? It is carbonic acid. H2CO3, what is the name of H2CO3? Please write in the box. H2CO3. Please write in the box, what is H2CO3? Carbonic acid. Yes, good. Tamanna? And its base, its salt with a strong base is NaHCO3 minus. Then, if we take basic or alkaline buffer, it is a weak base and it's salt with strong acid. So NH4OH. Example is NH4OH, ammonium hydroxide plus NH4Cl, means ammonium chloride. It's salt with strong acid, this NH4Cl, and this is a weak base. So buffers are always weak acids and weak base. A buffer may be defined as a solution of weak acid and its salt with a strong base. Is it clear to all of you? Please write. Have you understood about buffers? Please write in the box. Vikas, please write in the box. Vikas Kumar Dhaka. Then Nitesh Chaudhary. Have you understood the concept of buffers? Do you hear me? Am I audible to all of you? Okay. So our buffer may be defined as a solution of weak acid and its salt with a strong base. Then this is a first line of defense. Two most common chemical buffers. First is biocarbonate. You all know bicarbonate, and another is non-bicarbonate. First is the category of bicarbonate. You all know HCO3 minus, and other is non-bicarbonate. Means it includes hemoglobin, proteins, and phosphate buffer. Buffer or blood buffer system acts instantly, regulate pH by binding or releasing H plus, as I told earlier. Regulate pH by binding or releasing H plus, and the buffer cannot remove H plus ion from the body, but it temporarily acts as a shock absorbent to reduce free H plus ions. So it reduces free H plus ions. Buffers are of two types, bicarbonate and another is non-bicarbonate. It includes hemoglobin, proteins and phosphates. First buffer is carbonic acid bicarbonate buffer system. You all know H2CO3 is carbonic acid, bicarbonate HCO3 minus. So sodium bicarbonate, this is a salt, carbonic acid H2CO3, this is a salt, sodium bicarbonate. NaHCO3 is the most predominant and extracellular buffer system of ECF, extracellular fluid, we can say plasma. So most important extracellular buffer system of our body is, please write in the box, most important predominant extracellular buffer is what? Please write in the box. Am I audible to all of you? Yes, this is carbonic acid bicarbonate buffer system, or we can say bicarbonate buffer system. NaHCO3, its salt is sodium bicarbonate. Most body cells constantly generate carbon dioxide. You all know CO2. Most carbon dioxide is converted to carbonic acid. You all know, which dissociates into H plus and bicarbonate ions. So most CO2 is converted into carbonic acid, that is H2CO3, and H2CO3 is dissociates into H plus or HCO3 minus or its salt, either sodium bicarbonate, that is NaHCO3. So it prevents change in pH caused by organic acid or fixed acids in ECF, or functions only when respiratory system and respiratory control systems or centers are working normally. So is it clear about carbonic acid bicarbonate buffering system or buffer system? Blood pH and ratio of bicarbonate, that is HCO3 minus to H2CO3. The plasma bicarbonate HCO3 minus concentration is around 24 millimole per liter. Carbonic acid is a solution of CO2 in water, so its concentration is given by the product of PCO2, arterial partial pressure of CO2, that is 40 millimeter Hg, and the solubility constant of CO2 is 0.03. So by this Henderson-Hasselbalch equation for bicarbonate buffer, we can calculate the pH of blood. Substituting the values, like blood pH is 7.4, pKa for H2CO3 is 6.1, bicarbonate 24 millimole per liter, and H2CO3 is H2CO3 is equal to 1.2 millimole per liter. This 1.2 millimole per liter. So the blood pH is 7.4. The ratio of bicarbonate to carbonic acid is 20:1. Please remember this data, that the ratio of bicarbonate to carbonic acid is 20:1. 20 ratio 1 or 20:1. So what is the ratio of bicarbonate to carbonic acid? Please write in the box. Please write in the box. What is the ratio? Kanchan Bishnoi, Lalit, Kapil Kumar, Pankaj Yadav. This is 20:1. Okay. The bicarbonate concentration is much higher, 20 times, than carbonic acid in the blood. So is it clear? This statement is justified or not? This statement is justified or not? The bicarbonate concentration is much higher, around 20 times than carbonic acid, that is H2CO3 in the blood. This is referred to as alkali reserve. So please remember the definition of alkali reserve. What is alkali? What is an alkali reserve? So is it clear to all of you? When blood pH is 7.4, the ratio of bicarbonate to carbonic acid is 20:1. The bicarbonate concentration is much higher, 20 times than carbonic acid in the blood. So this sentence is justified? Okay, clear. It is called as alkali reserve. Next buffer is phosphate buffer system. It is also an important buffer system. Consists of anion H2PO4, a weak acid having pKa 6.8, works like the carbonic acid bicarbonate buffer system. It is mostly an intracellular buffer. Please remember, this is an intracellular buffer. So which one is an intracellular buffer? Please write in the box. Which one is intracellular buffer? Sodium dihydrogen phosphate and disodium hydrogen phosphate. You can see here sodium dihydrogen H2 phosphate PO4 minus and disodium hydrogen phosphate, that is Na2HPO4, constitutes the phosphate buffer. Okay. Next buffer is protein buffer system. The plasma proteins and hemoglobin constitute the protein buffers. The buffering capacity of protein is dependent on the pKa of ionizable groups of amino acids. The imidazole group of histidine having pK 6.7 is the most effective contributor of protein buffer. Please remember the pK of histidine, that is 6.7. And which group contributes it? This is imidazole group of histidine. Next is the hemoglobin buffer system. As I told you that it includes a protein buffer system. Heme plus globin protein is the only intracellular buffer system with an immediate effect on ECF pH. Helps prevent major changes in pH when plasma PCTO is rising or falling. Hemoglobin binds to H plus ion and helps to transport CO2, you all know, as HCO3 minus with a minimum change in pH. In the lungs, hemoglobin combines with oxygen. H plus ions or hydrogen ions are removed, which combines with bicarbonate to form carbonic acid. You all know is dissociates to release CO2 to be exhaled. So it means hydrogen ions are buffered by hemoglobin molecule. Please remember this line. Hydrogen ions are buffered by hemoglobin molecules by binding to H plus ions. So in the lungs, hemoglobin combines with oxygen. H plus ions are removed, combined with HCO3 minus or bicarbonate to form H2CO3, and this dissociates to release CO2 to be exhaled. So you all know the process which is involved in lungs, which occurs in lungs. You all know the enzyme carbonic anhydrate. You all know HCO3 minus, that is bicarbonate, carbonic acid, and CO2. Which enzyme is important in this reaction? Please write in the box. Carbonic anhydrase. Please write in the box which enzyme is important. Carbonic, yes. So carbonic anhydrase. Due to lack of aerobic metabolic pathway, RBC produce very little CO2. If lack of aerobic metabolic pathway, or we can say anaerobic pathway, the plasma CO2 diffuse into, please remember this word, the plasma CO2 diffuses into RBC along the concentration gradient. It combines with water to form H2CO3, that is carbonic acid, as I told earlier, by the enzyme carbonic anhydrase in the lungs. in this RBC. In RBC, H2CO3 dissociates to produce H plus and CO3 minus. The H plus ions are buffered by hemoglobin, as I told earlier. As a concentration of HCO3 minus or bicarbonate increases in the RBC, it diffuses into plasma along with concentration gradient in exchange for the cations to maintain electric. This is chloride ions in exchange for chloride ions to maintain electrical neutrality. So this is referred to chloride shift. You all know. You have read in your physiology classes in respiratory system. Helps to generate bicarbonate ions. So you all know what is chloride shift. Please write in the box. As the concentration of bicarbonate increases in the RBC, it diffuses into plasma along with the concentration gradient in exchange for chloride ions to maintain electrical neutrality. So what is chloride shift? Please write in the box. What is chloride shift? The plasma CO2 diffuses into RBC and it combines with water. CO2 plus H2O form H2CO3 by the enzyme carbonic anhydrase in RBC. This whole process occurring in RBC. What is anion gap? The total concentration of cations, you all know, and anions is equal in the body fluids. It is required to maintain electrical neutrality or balance. The commonly measured electrolytes are sodium, potassium, chloride ions, bicarbonate ions. So sodium and potassium together constitute about 95% of the plasma cation. You all know these are cations, and chloride and bicarbonate ions are major anions. So sodium and potassium ions are plasma cations, and chloride and bicarbonate ions are plasma anions and contributing to about 80% of the plasma anions. The remaining 20% of plasma anion include proteins, phosphates, sulfates, urates, and organic acid. You all know. So what is anion gap? Anion gap is defined as the difference between the concentration of measured cation, sodium and potassium, and that of measured anion, that are chloride and bicarbonate ions. The anion gap in fact represents the unmeasured anion in the plasma, which may be calculated as above by substituting the normal concentration of electrolytes in milliequivalents per liter. Anion gap in healthy individual, in human beings, is 15 milliequivalent per liter. You can see here. This is 100 plus 25 plus A minus. And this is sodium and this is potassium. Acid-base disorder associated with alteration in anion gaps. We will discuss it later. What is the importance of this anion gap? It is important in the disturbances of acid-base balances or disturbances in acid-base balance and its diagnosis. So the difference between the total concentration of cations and that of measured anion is called as anion gap. So is it clear to all of you? What are the major cations? Please write in the box. What are the major cations? What are the major cations? Please write in the box. Sodium and potassium. And major anions. Please write in the box. What are the major anions? And the difference between total concentration of measured cations, sodium and potassium, and that of measured anions is called as anion gap, and it is important, or it is associated with acid-base disorders. So is it clear to all of you? Yes, please write in the box. Is it clear to all of you? Have you understood the acid-base balance, buffering system, buffer system, and this anion gap? Okay. So first mechanism or first line of defense is buffer, and second line of defense is respiratory acid-base control mechanism or respiratory control mechanism or regulation. When chemical buffers alone cannot prevent changes in blood pH. The respiratory system is the second line of defense against changes. How eliminate or retain CO2? You all know, in the lungs. What is the major organ of this respiratory system? Please write in the box. What is the? Yes, lungs. So eliminate or retain CO2, change in pH are rapid. It is very important. This is rapid in nature. This is rapid. Occurring within a minute, respiratory system provides a rapid mechanism for maintenance of acid-base balance, and this is achieved by regulation of concentration of carbonic acid in the blood. So please remember this word. This is regulated, or this is achieved by regulating the concentration of carbonic acid, H2CO3, in the blood. Is it clear to all of you? By elimination or retain CO2, it is achieved by regulating the concentration of H2CO3. The large volumes of CO2 produced by the cellular metabolism activity endanger the acid-base equilibrium of the body. All of this CO2 is eliminated from body in the expired air via the lungs. You all know the rate of respiration is controlled by respiratory system located in the medulla of the brain. So where this respiratory system or center is located, please write in the box where it is located. Yes, medulla. The center is highly sensitive to changes in the pH of blood. Decrease in blood pH causes hyperventilation to blow off CO2. So please remember, decrease in blood pH causes hyperventilation. Compensatory mechanism. It adopts compensatory mechanism, that is hyperventilation to blow off CO2 and reducing the H2CO3 concentration, that is carbonic acid concentration. Hydrogen ions are eliminated as H2O. Respiratory control of blood pH is rapid, but only a short-term regulation process, since hyperventilation cannot proceed for long. So this, the diagrammatic representation of the regulation by lungs or respiratory regulation. Plasma, erythrocytes. Here you can see CO2 plus H2O, RBC. In RBC, this enzyme carbonic anhydrate, it forms H2CO3. And again, it dissociates into CO3 minus, that is bicarbonate, and H plus. It is hemoglobin buffer system. So by chloride shift, you can see here HCO3 goes to plasma and Cl chloride goes to RBC. This is chloride shift. Is it clear to all of you? Please write in the box. This is plasma or blood. Is it? It is RBC. So we can see here this acid-base balance, carbonic acid, bicarbonate buffer system. You all know CO2H2O. CO2 plus H2O, H2CO3, carbonic acid. This is reversible. You all know. Then again, this is a simple or normal process. It forms carbonic acid. Then again, it dissociates. This bicarbonate reserve. When fixed acids or organic acids and add H plus, means addition of H plus. So it combines with this HCO3 and form H2CO3, that is carbonic acid, and this again forms carbon dioxide and water. In the case of acidosis, means addition of H plus or pH is decreased. You can see here this interaction among the carbonic acid bicarbonate buffer system and compensatory mechanism in the regulation of plasma pH. You can see here this increased respiration by which it lowers PCO2, means hyperventilation in the case of acidosis, as I told earlier. In the case of alkalosis, decreased respiratory rate or hypoventilation, it elevates PCO2. and this removal of H plus. So this is the case of alkalosis. Interaction among the carbonic acid bicarbonate buffer system and the compensatory mechanism in the regulation of plasma pH. So you can see in the case of acidosis, hyperventilation is there, and in the case of alkalosis, hypoventilation is there. Next is last one, renal mechanism for pH regulation. The kidney plays an important role in the regulation of pH. Normal urine pH is around 6. You all know the pH of urine vary from 4.5 to 9.8. How it can be possible, or the regulation by kidneys or renal system? The kidneys are the third line of defense against wide changes in body fluid pH. First is buffer, second is respiration, and third is via kidney or renal acid-base control mechanism. Movements of bicarbonate, you all know, retention or excretion of acids via kidney or generating additional buffers. Long-term regulator of acid-base balance, it is an important line because respiration is short-term regulator of acid-base balance. May take hours to days for correction. Role of kidney is preservation of body's bicarbonate store. So this is an important line. Role of kidney is preservation of body's bicarbonate stores, HCO3 minus, accomplished by reabsorption of 99.9% of filtered bicarbonate, or regeneration of titrable bicarbonate by excretion of titrable acidity, mainly phosphate, and ammonium salts. These are the three processes. So renal regulation of pH by excretion of either excretion of H plus ions or hydrogen ions, reabsorption of bicarbonate ions, excretion of titrable acids, excretion of ammonium ions. Four processes are included in this renal regulation of pH: excretion of H plus ions, reabsorption of bicarbonate ions, excretion of titrable acid, and excretion of ammonium ions. We will take one by one in coming slides. First is excretion of H plus ions or hydrogen ions. Kidney is the only route through which the H plus can eliminate from the body. You all know hydrogen excretion occurs in the proximal convoluted tubules PCT and is coupled with generation of bicarbonate ions. Carbonic anhydrous catalyzes the protection of H2CO3 from CO2 and H2 in renal tubular cells. H2CO3 then dissociates to H plus HCO3 minus, means bicarbonate ions. H plus ions are secreted into tubular lumen in exchange for sodium ion. Sodium in association with bicarbonate is reabsorbed into blood. So main function is, aim is excretion of hydrogen ion. An effective mechanism to eliminate hydrogen ion from the body with a simultaneous generation of HCO3 minus, and hydrogen combines with non-carbonate base and then excreted. So this is the whole mechanism you can see here in renal tubular cells and this renal tubular tubes, tubular lumen, and this renal tubular cells. Sodium, and by this CO2 plus H2, you can see here forms H2CO3 in the presence of Ca, and then this again dissociates into HCO3 minus plus H plus, and this HCO3 comes out from renal tubular cell, and by this you can see here tubular lumen, sodium, then this H plus B minus by hemoglobin, this is excreted. So H plus excretion occurs in the proximal convoluted tubules. You all know carbonic anhydrous catalyze the protection of carbonic acids, and again it dissociates into H plus HCO3 minus. Main aim is sodium in association with HCO3 is reabsorbed into blood, and H plus ions are secreted into tubular lumen. So here you can see H plus ions are secreted into lumen. This H plus is secreted into lumen, and this sodium ions from tubular lumen goes to renal tubular cells or absorbed by this renal tubular cells. So two purposes. First is sodium ions are secreted into tubular lumen, and another is HCO3 is reabsorbed into blood. So you can see here SCO3 minus bicarbonate reabsorbed, sodium reabsorbed, and this H plus is secreted. So is it clear to all of you? Please add in the box this whole excretion of H plus ion. Have you understood the whole process? Yes, please add in the box. Okay. By this tubular lumen, sodium reabsorbs, H plus excreted, and this HCO3 also reabsorbs and goes to the blood. Reabsorption, another second process is reabsorption of bicarbonate. First is excretion of hydrogen ion, another is reabsorption of bicarbonate. This mechanism is responsible to conserve blood bicarbonate with simultaneous excretion of H plus ions. Bicarbonate freely diffuses from plasma into tubular lumen. Bicarbonate combines with hydrogen ion secretes by tubular cell to form H2CO3 carbonic acid, and then carbonic acid is then cleaved to form CO2 and H2O. As the CO2 concentration builds up in the lumen, it diffuses into the tubular cell along the concentration gradients, and in the tubular cell, CO2 again combines with H2O to form carbonic acid, which then dissociates into hydrogen ion and HCO3 minus. The H plus is secreted into the lumen in exchange for sodium. The HCO3 is reabsorbed into plasma is in association with sodium, as I said earlier, and reabsorption of bicarbonate is a cyclic process with the net excretion of hydrogen or generation of new bicarbonate ions. This mechanism helps to maintain the steady rate and will not be effective for the elimination of H plus or generation of new HCO3. So you can see here reabsorption of bicarbonate. This is tubular lumen, this is renal tubular cell, and this is plasma. You can see here sodium reabsorbs and then again goes to blood, and this HCO3 again goes to blood, and this H plus is excreted, and then it again combines with H2 combined with this H plus, then combines and form H2CO3, again CO2 plus H2O, and this CO2 goes to this renal tubular cell, and this process, this cycle is going on. Sodium, this sodium in tubular luminal plasma, HCO3, H2 HCO3 plus minus plus H plus. H plus is excreted into tubular lumen. This and this again forms H2CO3, and it again dissociates into CO2. CO2 comes into renal tubular cell, and again this whole process, this it's form HCO3 minus or bicarbonate ion, and this goes to into the blood. So sodium reabsorption of bicarbonate with the sodium. Is it clear to all of you? Reabsorption of bicarbonate. Next is excretion of titrable acid. Titrable acidity is a measure of acid excreted into urine by the kidney. Titrable acidity refers to the number of milliliters of N by 10 NaOH required to titrate 1 liter of urine to pH 7.4. Please remember this definition, titrable acidity. You have already read in your physiology classes. Titrable acidity reflects the H plus ions or hydrogen ions excreted into urine. So titrable acidity reflects the hydrogen ions excreted into urine. Excretion of titrable acid. Hydrogen ions are secreted into tubular lumen in exchange for sodium ions. This sodium ions is obtained from the base disodium hydrogen phosphate, that is Na2HPO4. This combines with hydrogen to produce the acid sodium dihydrogen phosphate, that is NaHPO4, in which form the major quantity of titrable acid in urine is present. Tubular fluid moves down the renal tubules, more and more hydrogen ions are added, resulting in the acidification of urine, causes a fall in the pH. So more acidic, fall in the pH of urine is more, as low as 4.5. So is it clear? More acidic means, what is the meaning of more acidic? Please add in the box. Falling the, yes, pH. So you can see here excretion of titrable acid. This is tubular lumen, this is renal tubular cell. Na2PO4. This gives NaHPO4, sodium. Sodium reabsorbs in renal tubular cells and it goes to blood. And it again, this NaH2PO4 excreted, and this, you can see here, this H plus is excreted into tubular human. And again, this by the enzyme H2CO2, H2O plus CO2, H2CO3, and this dissociates into HCO3 minus plus H plus. So HCO3 again reabsorbs, sodium reabsorbs, and this H plus is excreted. The excretion of titrable acidity by this Na plus NaHPO4, this H plus here, this combines with this NaHPO4 and this NaH2PO4 is formed. It is excreted. Excretion of this titrable acid. Last is excretion of ammonium ions in the renal regulation. The hydrogen ion combines with ammonia to form ammonium ion. You all know NH4 plus. The renal tubular cells deaminate glutamine to glutamate and ammonia by the action of enzyme glutaminase. The liberated ammonia diffuses into tubular lumen where it combines with hydrogen to form ammonium. Ammonium ions cannot diffuse back into tubular cell and excreted into urine, you all know. So this is the diagrammatic representation of this excretion of ammonium ions. This is tubular lumen. This is renal tubular cells. You can see here glutamine, glutamate. This ammonia excretes into or goes into tubular lumen, NH3, and by this excretion of H plus, it forms ammonium ion and it is excreted. So by this H2O plus CO2, H2CO3, by the enzyme Ca, then HCO3 or bicarbonate ion goes to blood or plasma, and this sodium also, sodium ions cations goes to blood, but this H plus is excreted into tubular lumen and then this ammonium ions are excreted. So is it clear to all of you? Excretion of ammonium ions. The basic thing is sodium reabsorbs, bicarbonate reabsorbs hydrogen ions, and titrable acidity or excretion of ammonium ions occur in the or by the renal regulation of acid-base balance. So now we will take disorders of acid-base balance. Today's main topic is disorders of acid-base balance and its diagnosis. So the acid-base disorders are mainly of two type. First is acidosis. You all know, decline in blood pH. Here, please remember the definition of metabolic acidosis and respiratory acidosis. Again, metabolic alkalosis and respiratory alkalosis. Alkalosis arise in blood pH. So what is metabolic acidosis? Due to decrease in bicarbonate, that is HCO3 minus. And what is respiratory acidosis? Due to an increase in carbonic acid, that is H2CO3. So again, when it decrease in metabolic acidosis, it increase in metabolic alkalosis. It increase in respiratory acidosis, it decrease in respiratory alkalosis. So in the case of acidosis, bicarbonate, you have to remember the word bicarbonate, and in the case of alkalosis, you have to, in the case of respiratory, you have to remember carbonic acid. Metabolic means bicarbonate. In both the cases, you can see here metabolic acidosis, decrease in bicarbonate, metabolic alkalosis due to increase in bicarbonate, and in this respiratory acidosis, increase in carbonic acid, H2CO3, and this respiratory alkalosis is due to decrease in carbonic acid. So please remember this word metabolic and this word respiratory. Metabolic relates with bicarbonate and respiratory relates with carbonic acid. So have you understood the whole definitions? Metabolic acidosis, respiratory acidosis, metabolic alkalosis, respiratory alkalosis. So kick in the pH. Is this pH up? pH 7.4. this and this. Slide in this. You can see here pH down below 7.4. Comparison between different types of acidosis and alkalosis. Clinical conditions, you can see here various conditions: metabolic acidosis, diabetes mellitus, starvation, lactic acidosis, respiratory acidosis, damage of CNS, brain damage, emphysema, metabolic alkalosis, pyloric obstruction, excess loss of HCl, respiratory alkalosis, stimulation of respiratory center, high altitude, and so here important are, you can see here, you can see from Satyanarayanan, the examples of metabolic acidosis are diabetic mellitus. You all know it is ketoacidosis. We will study in detail later. And other examples are renal failure, lactic acidosis, severe diarrhea, renal tubular acidosis, metabolic alkalosis, severe vomiting, hypokalemia, intravenous administration of bicarbonate. And these are the examples of respiratory acidosis: severe asthma, pneumonia, cardiac arrest, obstruction in airways, chest deformities, depression of respiratory centers by drugs like opiates. And these are the examples of respiratory alkalosis: hyperventilation, anemia, high altitude, and salicylate poisoning. So please remember these examples for your examination purpose. Metabolic acidosis, foremost important example is diabetes mellitus, which is ketoacidosis. For metabolic alkalosis, severe vomiting and hypokalemia. Respiratory acidosis, asthma and pneumonia. And respiratory alkalosis, hyperventilation, anemia, and high altitude. Here I have summarized metabolic acidosis, DM, ketoacidosis, lactic acidosis, renal failure, respiratory acidosis, severe asthma, cardiac arrest, metabolic acidosis, alkalosis, vomiting and hypokalemia, and respiratory alkalosis, hyperventilation, and severe anemia. This is an important slide because this shows acid-base disorders along with the concentrations of bicarbonate and carbonic acid in plasma. So, one by one, we will take. In the case of metabolic acidosis, pH is decreased or increased? Please write in the box. pH is decreased or increased? Please write in the box. Am I audible to all of you? Yes. So, in the case of metabolic acidosis, in acute condition, blood pH is decreased. So, here you can see HCO3 minus and H2CO3 minus. HCO3 minus decreased or increased? Yes, this will decrease. And this is normal. So, increased, you can see here, decreased, normal, marginally decreased, and marginally increased. So you can see here in the case of acute metabolic acidosis, pH is decreased. So what is the compensatory mechanism, or how it is compensated? It is compensated by hyperventilation. As I just told you in the previous slides, it is compensated by hyperventilation. Means by this hyperventilation, it may be normal, and SCO3 decreases, and this H2CO3 also decreases. By this H2CO3, HCO3 minus or bicarbonate decreases, and H2CO3 also decreases. It means blood pH may be increased, or we can say this is the compensatory mechanism, because in the case of metabolic acidosis, it shows low pH. Again, in the case of respiratory acidosis, acidosis are of two types. First, metabolic acidosis and respiratory acidosis. In the case of acute respiratory acidosis, you can see again here blood pH is low. Then HCO3 may be normal, and this H2CO3 you all know. You have to remember the word respiratory, and respiratory means, write down, respiratory means, yes, carbonic acid. Respiratory means carbonic acid. Okay. So Here you can see carbonic acid increases. So by the compensatory mechanism, or it is compensated by HCO3 minus retained by kidney. Yeah, it means bicarbonate ions retained or reabsorbed by kidney. So by this compensation or this process, you can see here blood pH may be normal, or this HCO3 minus increases and this H2CO3 also increases. It means HCO3 upon HCO3 minus upon H2CO3. It means when HCO3 bicarbonate also increase with the increase of H2CO3, it may be the condition may arrive to the normal. So this is the compensatory mechanism, or it is compensated by the retention of bicarbonate by kidney. This is hyperventilation, metabolic acidosis. The word you have to remember this bicarbonate. In the case of respiratory, you have to remember the word carbonic acid. Again, in the case of metabolic calculosis, you can see here in the case of acute pH. In the case of metabolic calculosis, pH gets increased or decreased. Please write in the box. This, yes, increased. It is increased. So you can see here HCO3 or bicarbonate ions increased, H2CO3 normal. So by the compensation, you all know by hypoventilation by lungs. Hypoventilation means decrease in the ventilation. So you can see here HCO3 minus upon H2CO3 or carbonic acid, HCO3 increases and H2CO3 also increases. When H2CO3 increases, it will occur, or the condition will arrive to the normal. So it is a compensatory process, or it is compensated by the process of hypoventilation. Next or last is respiratory alkalosis. You can see here in the case of acute respiratory alkalosis, pH is increased, then SCO3 bicarbonates are normal, then H2CO3 goes down. So by the mechanism of compensation by kidneys, it is compensated by increase in bicarbonate or excretion by kidney. Means increase excretion of bicarbonate by kidney. Here you can see retention and here you can see excretion. So in the case of metabolic acidosis, compensatory mechanism is hyperventilation. In the case of metabolic alkalosis, the compensatory mechanism is hypoventilation. And in the case of respiratory acidosis, retention of bicarbonate. And in the case of respiratory alkalosis, you can see here compensatory mechanism is increase excretion or increase in excretion of bicarbonate ions by the kidney. Now, have you understood the whole process of these four: metabolic acidosis, respiratory acidosis, metabolic alkalosis, and respiratory alkalosis? Please write in the box. Have you understood? Okay. So you can see here, this is the disorder. This is metabolic acidosis, primary change, decreased plasma bicarbonate, as I told earlier. And the compensatory mechanism is hyperventilation or decrease in PCO2. You all know. And the time scale for compensation is minutes to hour. Because this is a respiratory mechanism, and respiratory mechanism is faster. Then renal, you all know. And this metabolic alkalosis, you all know, increased plasma bicarbonate. Compensatory mechanism adopted by the body is hypoventilation, increase in PCO2. And this minutes to hour takes minutes to hour. Then respiratory acidosis, increase in PCO2. Or you can see it relates with carbonic acid. Elevation in plasma bicarbonate, increase in renal absorption of bicarbonate. This is the retention of bicarbonate, as I said earlier. You can see here in the case of respiratory acidosis, retention of bicarbonate. And in the case of respiratory alkalosis, you can see here decreased PCO2, reduction in plasma bicarbonate, decrease in renal absorption of bicarbonates, means excretion, increased excretion of bicarbonate ions. It takes days. So is it clear? So you can see here the another way of representing these acid-base disorders: pH low, increase, low, increase, H plus increase, H plus decrease, H plus increase in the case of acidosis, and in the alkalosis, H plus decreases. And primary disturbances and secondary responses, this is compensatory mechanism, you all know. First, by this secondary response, you can see here metabolic acidosis, the compensatory mechanism is hyperventilation or decrease in PCO2. Decrease in PCO2. And this is primary disturbances, means bicarbonate ions, decrease in bicarbonate ions, primary response. So likewise, this metabolic alkalosis, respiratory acidosis, respiratory alkalosis. By this hypo and hyperventilation, you all know. You can see here again this hyperventilation, decrease in PCO2, hypoventilation, increase in PCO2. And in this retention of bicarbonate, respiratory acidosis, and by this you can see here again retention of bicarbonate ions, compensatory mechanism, retention of or reabsorption of bicarbonate ion, and the case of respiratory alkalosis, you can see here excretion of bicarbonate ions or decrease in renal reabsorption of bicarbonate ions. So is it clear to all of you? So metabolic acidosis, reduction in bicarbonate leads to fall in blood pH. This is due to excessive production of organic acid, which can combine with NaHCO3 minus, or we can say bicarbonate, and deplete the alkali reserve. NaHCO3 plus organic acid, you can get sodium salt of formic acid and CO2. Commonly seen in diabetes mellitus or ketoacidosis. In the case of respiratory acidosis, the primary defect is due to retention of CO2, increase H2CO3, carbonic acid. You all know causes for respiratory acidosis are depression of respiratory center, pulmonary disorders, breathing air with high content of CO2. What is metabolic alkalosis? This is due to increase in bicarbonate concentration, occur due to excessive vomiting or an excessive intake of sodium bicarbonate for therapeutic purposes. Respiratory mechanism initiate compensation by hypoventilation. You all know, to retain CO2, this is taken over by renal mechanism, which excrete more bicarbonate ions and retain hydrogen ions. What is respiratory alkalosis? This is due to decrease in H2CO3 concentration, bicarbonate concentration. This is due to prolonged hyperventilation resulting in increased escalation of CO2 by the lungs. Renal mechanism tries to compensate by increasing the urinary excretion of bicarbonate ions. So acid-base disorders and plasma potassium. Plasma potassium concentration, normally 3.5 to 5 milliequivalent per liter, is very important as it affects the contractibility of the heart. You all know potassium. Potassium is cation or anion? Please write in the box. Potassium is cation or anion? Please write in the box. Yes. Hyperkalemia, you all know high plasma potassium concentration or hypokalemia, low plasma concentration can be life-threatening. It is related with diabetes, ketoacidosis or diabetic mellitus. Insulin increases potassium ion uptake by cells. The patient of severe uncontrolled diabetes with metabolic acidosis is usually with hypokalemia. You have to remember the word hypokalemia with this diabetic ketoacidosis. When such a patient is given insulin, it stimulates potassium entry into cell. This result is that plasma potassium level is further depleted. Hypokalemia affects heart functioning and is life-threatening. It is important. So it is related to diabetic ketoacidosis. Low plasma concentration of potassium, hypokalemia leads to an increased excretion of hydrogen ions and thus may cause metabolic alkalosis. So please remember, it causes metabolic alkalosis. Low plasma concentration of potassium, hypokalemia leads to metabolic alkalosis, and conversely, metabolic alkalosis is associated with increased renal excretion of potassium ions. means increased renal excretion means decrease in plasma. So is it clear to all of you? Here it is increased renal excretion of potassium. Here is low plasma concentration of potassium. When excretion is increased, plasma concentration is low, will be lower. So I will summarize the whole presentation. Have you understood the whole mechanism of acidosis and ketosis and this alkalosis, metabolic and respiratory? Please write in the box. Kriti, Meena, Kriti, have you understood the whole mechanism of these metabolic acidosis, respiratory acidosis, metabolic alkalosis, respiratory alkalosis? Kriti, Rahul Pawar, Supriya, Monica, Mayank Jain, have you understood? Am I audible to all of you? Have you understood the whole mechanism of this acid-base balance, disturbances, and their diagnosis? So what is the first line of defense of acid-base balance or acid-base disorders? Buffer, yes. So you can see here what is acid, what is base, you all know. Is hydrogen ion, acid, bases is OH minus or hydroxyl ions or combines with hydrogen ions. Acid-base balance, what is acidosis, what is alkalosis? Physiological state when pH is low or physiological state resulting from abnormally high plasma pH, it is called as alkalosis. Acidosis and alkalosis. Then what is acidemia and alkalemia? When plasma pH is lesser than 7.35, it is called as acidemia, and when it's greater than 7.45, it is called as alkalemia. Three different systems: blood buffers, respiratory mechanism, and renal mechanism. Buffer you all know. First important extracellular buffer is carbonic acid bicarbonate buffer. Ratio should be bicarbonate to carbonic acid is 20 to 1. And when the bicarbonate concentration is much higher, about 20 times than carbonic acid, it is referred as alkali reserve. Next, phosphate buffer, intracellular buffer, protein buffer, hemoglobin buffer, you all know. Then generation of bicarbonate by RBC. And what is anion gap? Anion gap is defined as difference between the total concentration of cations, sodium and potassium, and that of measured anion, chloride and bicarbonate ions. Anion gap in the healthy individual is 15 milliequivalent per liter. You can see here in the erythrocyte, the enzyme carbonic anhydrase, H2CO3, and again it dissociates into bicarbonate plus H+. This HCO3 comes out into plasma, and this Cl comes into RBC. Renal mechanism, can see here by 4 processes: excretion of hydrogen ion, reabsorption of bicarbonate, excretion of titrable acid, and excretion of ammonium ions. You can see here sodium reabsorption, bicarbonate reabsorption, and hydrogen excretion. Here you can see titrable acid and excretion of ammonia. Disorders are metabolic acidosis. Metabolic word is related to bicarbonate, and respiratory is related to carbonic acid. Acidosis decrease in pH and alkalosis increase in pH. These are the examples: metabolic acidosis, diabetic mellitus, diabetes, then respiratory acidosis, severe asthma, cardiac arrest, metabolic alkalosis, vomiting and hypokalemia, and hyperventilation and severe anemia are the example of respiratory alkalosis. This is an important slide. because it is compensated by this hyperventilation, this metabolic acidosis. You can see here respiratory acidosis. It is compensated by retention of bicarbonate ions, and this metabolic alkalosis is compensated by hypoventilation, and this respiratory alkalosis is compensated by increased excretion of bicarbonate ions by kidney. You can see here in detail. And this potassium is related to diabetes ketoacidosis, hypokalemia, and this hypokalemia causes metabolic alkalosis. Thank you. So now, have you understood the whole topic, this acid-base disturbances and its diagnosis? Please add in the box. Have you understood? Okay. Have you understood? Please add in the box. Am I audible to all of you? Okay. So thank you very much for listening me carefully. Thank you once again.